Good afternoon. My name is Costa and I'll present the work Trust and Reputation Multiagent-driven Model for Distributed Transcoding on Fog Edge. It's an application of trust and reputation models to solve a specific problem in a specific environment. We are following this agenda. We present our objectives. After that, a brief contextualization that continues with the analysis of our related work. Then we are presenting our proposal to solve the problem, and then 3 experiments that were elaborated to validate some assumptions we've made, and finally, final remarks and conclusions. Our objectives are 1. Define a trust and reputation multi-agent model for dealing with the problem of distributed transcoding of live video events over fog edge computing, and 2. Present a reputation-based node selection algorithm for selecting the best nodes to perform the transcoding tasks. First of all, what is fog edge computing? The FEC. FEC is a complement of the cloud computing, employing devices near the edge of the network, near our own devices, to reduce latency. Transcoding is a technique used to enable adaptive bitrate streaming, which is providing many bitrate versions of the same media, different quality versions, so the clients could choose the most appropriate of it due to their network conditions. As we can see, a signal is acquired and then split into segments and transcoded into destination versions, which every one of them must be provided and transmitted until reaching the viewers. This process consumes relevant computation resources, as the processing power of servers in the core, as network bandwidth for the backbone's black holes. The idea of distributing the transcoding jobs to the edge is to take advantage of computational resources available in the FEC, relieving providers for heavier processing network costs, offering better latency at the same time, which can result in an improved quality of experience for the viewers. Sometimes, transcoded versions are served only in a restricted area, or it is injected again in the content delivery networks, and maybe until the core, to reach a wider audience at the cost of the latency. We have looked at some related work, and overall, it was proposed a scheme employing roadside units to do the transcoding to serve a vehicle mobile network, where the problem of choosing the most appropriate bitrate version is modeled as a Markov decision process, and then a solution employing actor critic and deep reinforcement learning is tested. Below are all use the interrogated antenna radios of mobile networks to do the transcoding, chasing the objective of minimizing the content delivery network hits per stream. For choosing the best bitrate version, it's used a greedy algorithm. He, Zhang and Liu tried a crawled approach to minimize delay experienced by the users, proposing to select the nodes to do the transcoding based on their stability as viewers. After the previous work of He, Liu, Jiaxani, and Laboratory proposed that transcoding jobs were performed by nodes in the crowd and then rejected into network before the CDNs. The problem of selecting nodes and bitrate versions is jointly modeled as a non-convex integer programming problem. The present proposal is less attached to a specific network configuration. It has the objective of selecting the better nodes to perform the transcoding tasks, and the same way the quality of experience is observed, and based on viewers' automatic feedback, the trustworthiness of transcoder nodes are evaluated. Our proposal is composed of 3 agent roles. Transcoders are to do the transcoding tasks. The Viewer Proxy is a software agent which acts on behalf of viewers. It has a responsibility of monitoring the viewer gained utility and providing feedback to the broker, The broker has the responsibility of coordinating the process, collecting viewer proxies feedbacks, and then negotiating the transcoding tasks with the transcoder nodes. To do so, the broker has a layered architecture which employs trust and reputation pluggable models to evaluate the transcoder's performance. This is the utility function viewer proxies use. B is the length of the segment in bits. T is the duration of the segment in milliseconds. I is the interval spent playing the segment. If the segment was already in the player's intern buffer, it's equal to the segment duration. S will return 1 if the segment was downloaded and played, 0 otherwise. What it means? After some time trying to download the segment, eventually the player could give up and try the next segment. This will make this success function return 0. Beta is a constant, which represents how bad viewers judge interruptions. This is to give an idea of how the parameter beta could influence the accumulation of utility. We use the same data on varying the beta, and the result can be almost linear or kind of parabolic. In this slide, we show up the broker architecture, which is composed of layers. The belief database management just updates the database of transcoders when new transcoders register into the broker, or update the segment database when new video segments are added to the stream. Transcoder's evaluation works second these steps. 1. Some utility feedbacks received from viewer proxies. Those values are normalized in a range of -1 to 1, and then it turns to be a rating of a transcoder serving a segment to a viewer proxy. The ratings are fed up to a pluggable trust and reputation model. We have used the FAR trust and reputation model. The trust and reputation model then will transform those ratings in values that mean trustworthiness and reliability that will compose the transcoder evaluation. Transcoders evaluation are used in the negotiation layer, which employs some algorithm for selecting the transcoder nodes that will receive transcoding assignment offers. In this work, we used selecting methods that could do some balancing between exploration and exploitation tendencies, like our named algorithm. This is the pseudocode of our selecting algorithm, reputation-based node selection, ReNoS. The idea is selecting nodes proportional to their trustworthiness as transcoders. If the parameter factor is 2, the most trustable transcoder will be selected with 50% of chance, the second one with 25%, and go on. Probabilities is used here to allow some degree of exploration, and not just exploitation of the better transcoders. Experiments are designed to answer 3 questions. In which frequency does viewer proxy require new segments to the providers? How much processing power should the FEC node have to perform as a transcoder? And can ReNoS algorithm perform as well as other selecting algorithms? Say it differently, we want to know how much time do we have to do the job? How much time transcoders will spend by segment, and in the end, will our approach work? On the first experiment, we streamed the video Big Buck Bunny using for different durations in 2 different players, VLC and LOS.js, and we found out that requesting frequency is close to the segment duration, and the player's buffer algorithm does not have a big impact on it. Second, we tried 5 different transcoding methods to reduce bitrate in 3 different machines. And in the worst case, for 100 milliseconds, we have spent 400 milliseconds to achieve a 60% reduction. We have also confirmed that the best method to reduce the bitrate is reducing the screen size. the experiment 3. In the experiment 3, we developed a simulation of our proposal using the JADE framework. We use the fire trace repetition model. Then we simulate 100 segments of 2 seconds of duration with 1 broker, 3 transcoders, and 12 viewer proxies. Transcoders were set to different profiles, varying the upload speed. 2 of those profiles are good enough, the third are not. The third is not. Was not. Then we applied 3 different selecting algorithms to observe how each one would influence the accumulation of utility by viewers. The 3 algorithms were multi-armed bandits upper confidence bounds, our suggested algorithm ReNoS, and randomly choosing transcoders at each step. The best choice is if algorithms tend to assign fewer transcoding tasks to transcoder C, which is prone to making viewers accumulate less utility. So, naturally, random choice must perform worse when compared with the others. The experiment outcome confirmed our hypothesis using UCB and ReNoS. The simulated system performed much better than just choosing transcoders by chance, and UCB resulted in viewers accumulating more utility, although some statistical tests do not indicate there is relevant difference between the two ones. Two ones I say, ReNoS and upper confidence bound. When we looked at the assignments, we can see that both were able to identify the harmful transcoder of profile C, and we can see that our algorithm tends to do the load balancing in a more predictable way. Despite the fact of those outcomes are encouraging, we do recognize that further investigation in an environment closer to the real is necessary. In this work, we presented a multi-agent model for distributed transcoding on the FAQ. We explained how trust and reputation models can be used to deal with the risk of cooperation in the FSC. We presented our algorithm for selecting the bare nodes to do segment transcoding. And finally, we present experiments conducted to validate our assumptions.